First of all, yeah, thank you. On behalf of Bob, I'm not Bob, but we'll try to fill in for him as best I can here. This particular project was something that we've worked on. We've been working in this particular area for some time. And this is a project for the Electric Power Research Institute. We've done 2 or 3 phases or cycles of this kind of work for them. And we have a host of participating utilities. And we certainly thank and acknowledge all those folks over the years. But what we're looking at is using spray dryer absorber material. By spray dryer, what I'm talking about here is what I would call dry material, dry absorber, or semi-dry absorber, as opposed to normal scrubber material. So anyway, this is the talk. We'll get a little background introduction, material characterization work. All right, it's kind of standard outline of the talk. Basically, what we're looking at here is, like I said, the semi-dry systems. These are spray dryers. And there's a new generation of materials, of systems out there that sort of showed up in the last, sort of the end of the coal era, I guess, as I'd put it. And these are circulating scrubbers. Some of them are like entrained fluidized bed units. The wet systems you're all familiar with. Most of those utilize forced air oxidation. The semi-dry systems, the spray dryers, don't. They get a little bit different kind of mineralogy and chemistry. And their product is either dry or kind of dampish, some of them. It depends upon how they're run. And then there's the dry systems. The difference between the dry systems and the semi-dry systems is the dry systems are not necessarily co-current, the circulating units. You can put the moisture in at different places. From where you're injecting it, you can circulate it, you get a little bit higher use of it, and it's a little bit more flexible. So over time, they've seemed to kind of develop a following. Spray dryer systems are fairly simple, straightforward units. Up here, there is, you form a slurry, usually lime. Most of these are lime systems, and it'll come in perhaps as a pebble lime. You hydrate it, it's mixed in, and then these units spin at very high speeds, 5,000 RPM, and it creates this spray which moves countercurrent to the flue gas. And it does a reasonably decent job. It'll form a mixture of calcium sulfite or Bacchite, calcium sulfate, and it dries. It can be fairly effective, if it's well run. This is a typical installation. This was actually from some work that we did for AEP on some fouling issues at this particular plant. This is a big one. This is 30 meters in diameter. This is probably the biggest of the spray dryers that you can get right now. Typically, they're a little bit smaller than that. This actually has 2 units. For a 500 megawatt system. So, these are big. This particular system, by the way, had a recycle in it. Let me go back. Had a recycle in it, which was actually part of the issues with regard to the fouling. Some of it had to do with some of the recycling that was going on there. But you can kind of get a feel for what they look like there. So what we're kind of looking at is really what level, or can you use some of these materials in concrete? as a partial replacement for fly ash or any other material. So we've done a number of studies to take a look at that. One of the things that we wanted to look at was the effect of, part of the study was the effect of calcium sulfate or Bacchite on hydration. So I'll comment a little bit on that at the end of it. So the spray dryer material is a mix of fly ash and calcium-sulfur compounds. It depends upon the particular plant. Some plants will take the fly ash out and then run the flue gas through the spray dryer, okay? And then you can have a bag house. Some of it will some plants will take the fly ash and blow everything through the spray dryer and into another recovery. It's really got to do with pressure drops in the system and how it's designed. Okay, it's not necessarily optional after the plant is built how you want to do this, but there is that difference, and what you find then is that these materials reflected in their chemistry, reflected in their mineralogy. So you have this sort of high sulfate and kind of lower sulfate materials. Okay, so yeah, this is material characterization slide there. Okay, that's good. That's what we did. We took a look at, we've looked at a lot of these over the years, and we had participation, probably 7 or 8 utilities. But we're just going to boil this down to really 2 different kinds of materials. What we call a high fly ash, and that's a unit where the fly ash is introduced into the spray dryer and then collected with the spray dryer material. And what we call a low fly ash, and that the fly ash in this case is separated before the material goes into the spray dryer. So the fly ash is gone for the most part, not entirely, but there is some differences. The big difference, of course, is in the amount of calcium and silica and sulfate in this case. And then there is some differences in the free lime available. Because these things react fairly, a spray dryer, a lot of these units will give you 2 seconds. Okay, I was going to say 2,000 milliseconds, but anyway, 2 seconds of reaction time. It's things take place fairly quickly, and you end up with a fair amount of free lime in the system, which may or may not be of any use. But you can see from the silica and the calcium, there's quite a bit of difference in these 2 systems. Okay, so that's what we got. If you look at the high fly ash materials, it has a morphology that's not terribly different from fly ash. You see bits and pieces of sulfate in there, but you can still see a lot of fly ash. You look at the low fly ash materials with a lot of scrubber material in there. It has morphologically, it's quite different, and it generally is finer. We actually found we ran across one spray dryer unit that was all 3 micron and below. It was really fine. It was like face powder. But typically it's a little bit coarser than that. I think it depends upon how the lime is prepared. Like I said, a lot of these things kind of come in as pebble lime. So there is a difference in the particle sizes and the morphology of these materials. So this is mortar work, okay? And we looked at, this is looking at compressive strength over time, over a couple of 100 days, better part of a year. You can see the control up here I think is in the black, these are the low materials and our high materials, high flash and slow materials. Some of these materials actually exceeded the strength of the control, which was good. We had, reasonably good data here. They're kind of encouraging. The problem with these materials is the water demand. It doesn't give you the benefit of a regular F-ash or even C-ash, especially F-ash. In other words, the water demand goes up, not down. This is spray dryer material. Well, what's that? That didn't work. Stop it. Okay. Did that? Oh, there we go. I will not use my pointer on that. One thing that we did find is that the use of all of these materials had an impact on set time. They all acted to retard both the mortar and the concrete. So going back to that, this change in set time was also reflected in some of the mortar work. So this is looking at some of the materials and sulfur content versus glass content. You can see with the low fly ash materials, a lot of sulfur content, not as much glass. With the high fly ash materials, or the high fly ash materials, you've got a lot more glass. It's sort of common sense there. And that was also reflected in the behavior of these materials. So these are, okay, you formed a lot of these hydrated calcium carboaluminate phases in this material as well, probably as a reaction from the C-ash that's going on there. Dimensional stability, this is looking at mortar expansion. I believe this is, yeah, these are all still the mortar tests. They range from being kind of nasty here for that low fly ash. There was a lot of expansion to being fairly well behaved. Okay, and that was the higher fly ash materials. You can see it, the dry shrinkage and the expansion in both cases were. Most of the materials were okay. There was one or two samples that were quite wild. Some of the ones that were low flash behaved fairly well. It was a little bit of unpredictability in there. Looking at concrete work. These are various mix designs. These were not any exotic mix design. We're looking at, I think we're looking at pavement mixes here. We looked at both high and low sulfate. We had, fairly decent results over time. Anyway, these are the mixed designs. We use some air and training reagents, the same kind of thing you would do. This is the concrete performance over time. We used 20% substitution in the concrete. The performance in the concrete was fine. The one thing it did improve, we looked at both compressive and flexural strength. Compressive strength passed, and in most cases, the use of the spray dryer material improved the flexural strength. So that was a little bit unexpected, but nonetheless, even with the high sulfate control or the Bacchite over time. One of the things we found, we've examined these over a long period of time. A lot of people say, well, that the Hannah Bacchite is going to be a problem. It's expansive. What we found, though, if you look at it, it disappeared slowly. It's a simple oxidation reaction. You go from a sulfite to a sulfate. There's just oxygen. That's all you need. But it doesn't take place quickly. The Hannah Bacchite has about the same molar volume as basanite. So, you don't have that effect in there immediately. The other thing is that Hannah Bacchite, the sulfate, is very insoluble. Its solubility product is really low, maybe 10 to the minus 50. It's just something crazy. But when you oxidize it, it goes into one of the sulfate forms, gypsum, for example, which is fairly soluble. And that makes it somewhat labile. So the concrete set, it's got a lot of strength. This oxidation takes place slowly, and the system has a chance to move some of the sulfate around. It's still hydrated, and it wasn't what we expected. We didn't see a lot of blown up concrete. This is some of the durability. This is looking at resistivity, and we found this is a very good measurement that's fairly useful as well, looking at the different forms of it. Okay, so anyway, to summarize, we had reasonably good results, even with some of the high sulfate material. With this surface resistivity, we found that over time that the resistivity is a measure of pozzolanic activity. If it exceeds control, that's a very good measure of pozzolanic activity over time. Right now, we're working on, this is the latest plans for looking at this material in the field. This is some paving up in Chicago at Uzingas. I don't know if any of you guys from the Midwest or Chicagoland, you know them. They're big ready mix company. We've worked with on this in this area for some time. And this is the parking lot of one of their facilities. They're certainly not going to put this stuff in a highway. But anyway, we're going to, this year, we're going to look at a demonstration of these various, both high sulfate and low sulfate. We've lined up some EPRI members to work and participate in this. And this was scheduled. This was scheduled for a year ago. With the COVID thing, everything stopped, and we never got this off the ground. But as soon as we can get out in the field and do this again, we're going to do this demonstration. And this is they were going to repave this anyway, and so we're going to take a look at the spray dryer material over a period of time. And this will get some. This will be this standard paving mix, and this is going to see a lot of concrete. This is Zinga's fleet. This is going to be beat up with concrete mixtures. We'll see how it actually works in the field. Okay, so anyway. It's benefits of spray dryer absorbent materials. We got some reduction in clinker content, same as fly ash. Low energy, sustainable construction materials. I guess that's kind of a standard phrase. Mixing water achieves specified slumps, a slight early stage. Concrete made with spray dryer does achieve 28-day strength. We did meet the 28-day design strength. And the spray dryer ash collected with the fly ash in particular did improve resistivity, and which is consistent. I misspelled it. Consistent with pozzolanic activity. Okay, so anyway, it does maintain its pozzolanic activity. So anyway, thanks. It probably have been better to have Bob do this, but nonetheless, thanks for your time. We would like to also recognize the work was funded by the Electric Power Research Institute, and their support is always gratefully acknowledged. And of course, EPRI, the opinions expressed are those of the authors, not necessarily of EPRI. That's her standard disclaimer. So anyway, I'd like to thank those folks as well. So that's it.